In today's lesson, we're going to look at the three main types of reaction encountered in organic chemistry and then the mechanisms associated with them. The three main types of reaction can be sort of divided into number 1, addition reactions, number 2, substitution reactions, and number 3, elimination reactions. Addition reactions must always involve a double bond or a triple bond, so something unsaturated combining with another species to produce a product. Just very generally, if I just use the displayed structure of a double bond there, plus some molecule A, B, then the molecule adds to the double bond to produce A, B, and you can see in this case two things have become one. So whenever you see a double bond becoming a single bond, a saturated product, it's more often than not going to be addition. Now, the next one, substitution, this is quite easy to spot as well. So basically two things turn into two new things. So real sort of general language there. So what do I mean by that? So say we've got a molecule where you've got atom A on the end and then it's reacting with reactant B. You will see the molecule remain exactly the same apart from A has been swapped out for B and A has been ejected or substituted. So you can say, so going back to what I said originally, two things have become two new things. And like the first example with addition, where you've got two things turning into one, this is not the case for substitution. And then elimination is actually kind of related to addition, because addition involves the removal of a double bond, whereas elimination reactions produce a double bond. So, for example, dehydration reactions, cracking reactions. So you start off with a saturated molecule, again only showing part of the molecule, so maybe it's got P and Q, two atoms attached to that saturated molecule, and then a double bond is produced, and then molecule PQ leaves as one thing. So you always see the production of a double bond. Look out for maybe an alcohol being dehydrated to an alkene plus water kicked out, or another really popular one. A common example would be like a haloalkane, where hydrogen halide like HCl or HBr would be removed. And again, you get in the production of that double bond. Once you've decided it's addition, substitution, or elimination, the next thing to decide is this bit here, which is the type of mechanism. You're going to be classifying the mechanism as either electrophilic or nucleophilic. What are the permutations for that? So electrophilic addition, electrophilic substitution, nucleophilic addition, nucleophilic substitution, and then elimination is neither electrophilic or nucleophilic. There may be electrophiles and nucleophiles participating in the reaction, in the mechanism itself, but you don't hear the phrase electrophilic elimination or nucleophilic elimination. It's just elimination. Right, so I think at this point, probably a good idea to classify what an electrophile is. An electrophile, sometimes written as just E+, is defined as an electron pair acceptor, and for that reason, it is therefore going to be electron deficient. What does that mean? It's likely going to be carrying a positive charge. For example, a carbonyl group is probably the best example, where you have a delta positive, delta minus. So the E plus, the electrophilic part of that would be the carbon delta plus. It could be a full-blown atom, like a metal positive ion, or it could be any other source of positive charge on a molecule which something electron-rich is drawn to. Maybe it could be even just a CX bond where X could be a halogen or something more electronegative, and you've got that positive charge there. So it's an electron pair acceptor and it's electron deficient. So a nucleophile is defined as, it's the exact opposite. So it's an electron pair donor and thus is electron rich. Nucleophiles can be charged. For example, cyanide, Cn minus, hydroxide's a really good one, thiocyanide, and so on. So these are carrying a negative charge, so can sometimes be considered as a more potent nucleophile. And then you've got neutral nucleophiles like water with a lone pair in the oxygen, ammonia, and so on. Now that we've defined nucleophile and electrophile, we then can return back to this and we need to decide then, for example, you're looking at a random equation Is this electrophilic addition? Is this nucleophilic substitution? How do we do this? Right, the rule is this. Number one, decide if it's, you just look at the reaction, decide if it's addition, elimination, substitution. That should be fairly obvious from looking at these sort of templates and seeing, what is going on in the reactions. Is it two things becoming one? Is it two things turning into two new things? And then you can decide, is it addition, elimination, substitution? Once you've determined that, the next thing to do is, number two, you need to look at the species. Species being just a general word we use in chemistry to describe something reacting. It could be a free radical, it could be a molecule, it could be an ion, it could be, a much larger molecule. It's just the other thing reacting with the organic molecule of interest. So you look at the species reacting with the organic molecule. If I just underline in green, what do I mean by species? So that would be that thing there, or that species there, and so on. It doesn't apply to elimination. For addition and substitution, this is concerned with. And then you just follow this rule. So once you've looked at that species reacting, you think, right, does it have a positive charge, a full-blown positive charge, or some sort of dipole with a delta plus, delta minus? If it does, then it's going to be electrophilic. And then if the reactant species has a lone pair, or an obvious negative charge, then it's going to be nucleophilic. So then it would be nucleophilic substitution or nucleophilic addition. Now, this might not be obvious from the reactant for electrophilic, but in the first stage of the mechanism, you will see the organic molecule attacking a delta positive charge or a full-blown charge, and that first step, that's what would classify it as electrophilic. But generally, you just look at the molecule reacting with the organic, and if it's got a delta plus charge or a full-blown charge, it's going to be electrophilic, and then if it's a lone pair or a negative charge as well, it's nucleophilic. Classify the following reactions. So we have A, which is bromoethane plus sodium ethoxide goes to product, which is an ether, plus sodium bromide. So immediately I can see that two things are turning into two new things. What fits that definition? Well, I've just written it there. It's substitution. So it's something substitution. Then the next thing I need to do is look at the molecule reacting with the organic. That's the organic molecule. And this is the reactant species there. And I can see it contains a metal and a non-metal part. So I just mentioned earlier that it's a salt. So that's made up of Na plus O CH2 CH3. Now let's look at this bit. This is the bit that has ended up reacting with the organic molecule, right? How do I know that? Because there it is. And immediately I can see it has a negative charge. So that means it's going to be a nucleophile. So it's a nucleophile attacking this organic molecule bromoethane to produce sodium bromide plus the ether. So therefore it must be nucleophilic substitution. So you can see how I've deconstructed that second reactant there, looked at it carefully and looked at the part that actually reacts with the organic molecule, and immediately we see it's a minus charge, so it's going to be a nucleophile. So in this second one, I can see that formula there. Well, let's dig a bit deeper. What is that molecule? So that is actually unsaturated, and the way the formula that fits that is going to be, it's an alkene, but it's a double alkene. Just drawing that out, we have butadiene. And I can see that hydrogen is reacting with it to produce just one product. Two things are just becoming one product. The starting organic molecule is unsaturated, has double bonds. So immediately I can say this is going to be something addition. So now I need to classify it as nucleophilic or electrophilic. So now my attention turns to the hydrogen. And in the mechanism for addition reactions with hydrogen, what happens is the double bonds are the electron-rich species, and they attack the hydrogen, which has a polarized delta plus, delta minus induced dipole when that molecule moves nearby. In the same way like bromine, when you have a Br2 molecule, moves near the double bond and it induces a dipole. How can that help us? Well, when that happens, immediately the double bond then attacks the delta plus and then ejects the other part. That's all I need to know for the start of this mechanism, because in the very first stage, we can see that the electron-rich double bond is attacking the electron-poor delta positive hydrogen, what is the first bit that's attacked on the hydrogen? It's the delta positive. So that means it must be electrophilic. So again, deconstruct, take a little look at the molecule reacting with the organic, and look for that delta positive charge, look for the plus charge for it to be electrophilic. You may have to look at the first step of the mechanism, or if you've got a lone pair or a minus charge, then it's going to be nucleophilic. And that's how you can get to a strict sort of definition of the type of reaction you have when faced, with an unfamiliar reaction like that. Okay, thanks for watching. I hope that was helpful. Please like and subscribe. Check out all of the other content I've produced on organic chemistry. Lots of videos there to help you with your studies. And see you in the next one.